Assalamu alaikum dear students. I welcome you to 32nd lecture of probability and stochastic processes. In previous lecture we were talking about convergence. We talked about convergence of a sequence of numbers and convergence of a sequence of functions. While talking about convergence of a sequence of numbers, we said that if we have a sequence of numbers x1, x2, x3 and so on, then this sequence converges to a destination value x0 if we are given a limit of closeness, a small real number delta, then we can find a threshold index and all the numbers in the sequence with indices larger than this threshold index will be closer to the destination number than this limit delta, or the difference, the distance between the destination value and all the numbers with indices larger than the threshold index will be smaller than this delta, the limit of closeness. In last lecture we worked with two sequences of numbers, and you can see those sequences now on your screen together. The top sequence comes from a formula xn is equal to 1 over n. So all the numbers in this sequence are positive numbers and they monotonically decrease, and as the sequence progresses the numbers become smaller and smaller. So if you pick any threshold of closeness, any limit of closeness delta, then there will come a time that all numbers from a certain threshold index will be closer to the destination value, which is 0, by that delta, or the difference between the destination value, which is 0, and the numbers in the sequence after the threshold index will be less than delta. The other sequence came from a formula which was e raised to power minus n over 25 times cosine of n over 4. So this formula has two elements, an exponentially decaying element and an oscillatory cosinusoidal element. The multiplication of two gives us a decaying sinusoidal sequence of numbers. This sequence also converges to 0, but in an oscillatory manner. Sometimes the number that we get in the sequence is larger than the destination value 0, and sometimes this number is smaller. So in convergence of a sequence of numbers, we define the distance between the destination value and the elements of the sequence as the absolute value of the difference of two numbers. This is the only natural way to define distance between two real valued numbers. In last lecture, we also talked about convergence of functions. We were given a sequence of functions which were defined over a common domain, which was a subset of real numbers. And our convergence of functions was indirectly defined in terms of convergence of sequence of numbers. We picked one element of domain and evaluated all the functions for that particular element of the domain, and we got a sequence of numbers. If that sequence of number converges for all elements of the common domain, then we say that the sequence of functions converges to a destination function. In addition to this point-by-point convergence of functions, which is defined indirectly as convergence of sequence of numbers, there are other convergence criteria. These convergence criteria are defined in terms of closeness of vectors and closeness of functions. And when we talk about closeness of vectors and closeness of functions, or distance between two functions or two vectors, we are effectively talking about norms. Norm of a vector or norm of a function is a real valued number assigned to that function or vector, and they are used to define the closeness of two vectors or closeness of two functions. The discussion of normed spaces is not included in this course, but you should study this topic briefly. Go to Wikipedia and search for normed spaces and just see the definitions of different norms. Let's have a look at the definition of norm of a finite dimensional vector. You can see this definition on your screen, and if we have a finite dimensional vector with capital N elements, then pth norm, which is represented by capital L with index p, of this vector x, which has capital N elements, is defined as sum of pth power of all the elements, and summation is then raised to a power of 1 over p, or a pth root is taken of the whole summation. This definition gives us different norms, and most commonly used norms are second norm or L2 norm, and for L2 the formula gives summation of squares of all elements followed by the square root of that summation. This is called Euclidean norm or second norm L2. There are other useful norms that are also used, and two of them are L1 norm, which is defined by just summation of all elements, and L infinity norm, which is defined as the maximum of the absolute values of all the elements in the finite dimensional vector. So if you have a finite dimensional vector, you can define its first norm, L1 norm, L2 norm, L3 norm, or any other norm up to infinity, where L infinity norm has a special definition. The norm of a finite dimensional vector gives us a measure of its distance from the zero vector, where the zero vector is a vector of all zeros. We can use norm of a finite dimensional vector to find the distance between two vectors of the same dimension. So if we have a vector x1 and a vector x2 defined in an n-dimensional space, then the distance between the two vectors is the norm of the difference vector, where difference vector is element by element difference of the two vectors. So a norm of a finite dimensional vector can be used to define the closeness between two vectors, or the difference or the distance between two vectors. Similarly, we can define norm of a function, where a function is defined over a finite subset of real line or the whole real line. The definition for norm of a function can be seen on your screen. It says that the pth norm, which is represented by small l, so LP norm of a function defined over a finite or infinite subset of real line is defined as integration of pth power of the function, and the result of integral is raised to 1 over p power, or pth root is taken of the result. This definition can be used to find commonly used norms, which are second norm or L2 norm, which is equal to integral of square of the function followed by square root of the result of the integration. Similarly, L1 norm is simply area under curve or integral of the given function, and L infinity norm for a function is the maximum value of the function over its whole domain. Just like finite dimensional vectors, norm of a function can be used to measure its distance from zero function, where zero function is a function with all values 0. And the norm of a function can be used to define the distance between two functions or closeness of two functions, and that is obtained by taking the pth norm, the second, the first, or L infinity norm of the difference function, where difference function is element by element difference of the two functions that are given. Now that we can define the closeness of two functions in terms of their pth norms, we can talk about convergence of random variables under different convergence criteria. You know that random variables are also functions. They are defined over sample space. So convergence of random variables can be under different LP norms. The first type of convergence that we are going to talk about is Shor convergence. The Shor convergence of random variables is defined in terms of element by element, point by point convergence of all the outcomes in the random variables. So if we have a sequence of random variables x1, x2, x3, and these random variables give outcomes, give values for any element of the sample space, and this sequence of numbers that are given by the sequence of random variables, if this sequence converges for all elements in the sample space, then we call this type of convergence as Shor convergence. So this element by element of convergence of a sequence of functions is Shor convergence in terms of random variables, and if we have a sequence of regular functions, that is convergence everywhere. Now the question is, what type of pth norm does this convergence follow? If you think carefully, then you will realize that this follows the L infinity norm. Why? Because the sequence of numbers for all elements of domain, whether it's a subset of real line in case of set of functions or elements of sample space in case of random variables, the sequence of numbers converges for all elements of the domain or the sample space. So if this sequence of numbers converges for every element, then we can pick a common delta, a common closeness limit. Then these sequences of numbers evaluated for different outcomes or different elements of domain will converge, and they will reach this limit of closeness for different values of threshold indices. If you take this whole collection of threshold indices, they will all be finite, because the convergence of a sequence of numbers requires that we find a finite threshold index beyond which the sequence of number has gone closer to the destination value than the limit of closeness. So all these numbers are finite. Then you take the maximum of this whole collection, and that is your threshold index beyond which all the sequences of numbers are closer to the destination value than the threshold limit delta that we started with. So when all these sequences has gone closer than delta, then the sequence of functions or sequence of random variables has gone closer to the destination function by a value which is smaller than delta. Hence it has converged for all the values, and the maximum value of the difference between the destination value and all the functions beyond this threshold index will be smaller than the delta. So we are taking L infinity norm of the difference between the destination function and the functions which have indices beyond the common threshold index, which is the maximum of the collection of threshold indices that we obtain out of the sequence of numbers that converge to destination numbers. I hope it's also clear that almost sure convergence in case of random variables or almost everywhere convergence in case of regular functions also follows L infinity norm, but on a restricted domain, because all elements of domain do not converge. So on the restricted domain everything converges, hence the sequence of functions or sequence of random variables for almost sure convergence follow L infinity domain. What about other types of convergences of random variables? We talked about convergence in probability, where we have random variables x1, x2, x3 and so on, and there was another destination random variable x0. We said that this sequence of random variables x1, x2, x3 and so on, converges in probability to x naught if for any positive number epsilon or delta, the probability of the difference between xn and x naught being smaller than that epsilon goes towards 0. Let's try to see what type of LP norm does this convergence in probability follow. Convergence in probability talks about difference of two random variables. One is the destination random variable and the other is one of the sequence given. So the new sequence of random variables is x1 minus x0, x2 minus x0, x3 minus x0, and so on. With this new set of random variables, the convergence in probability says that probability of this new sequence of random variable being away from this epsilon or delta region is going to converge. So probability is going to converge. The sequence of numbers obtained through integration of PDF of this new sequence of random variables is going to give us a sequence of numbers which is going to converge towards its destination. Since evaluation of probability of a difference between two random variables over a certain range, say minus epsilon to epsilon or minus delta to delta, is integration of PDF over the interval. Hence, this convergence uses L1 norm because it simply integrates the difference between the original sequence of random variables and the destination random variable over a certain interval. So sure convergence and almost sure convergence use L infinity norm, and convergence in probability uses L1 norm. So sure convergence and convergence in probability are different, and here we are going to see an example where this difference will come out very clearly. On your screen you can see a sequence of random variables. You see a horizontal line and then some vertical lines. This first vertical line represents the first random variable, then second, third random variable, fourth, fifth, and there are other random variables on this line. These random variables assume their values in a special manner. The first random variable always assumes a value 1. Then second and third two random variables are grouped together. A random variable is picked out of these two and it is assigned a value of half. The other is assigned a value of 0. Next set of three random variables are grouped together and one out of these three random variable is picked randomly and it is assigned a value of 1 over 3. The remaining two random variables are assigned value of 0. The next set of four random variables are also treated in the same manner. One of the four is randomly picked and assigned a value of 1 over 4. Other three are assigned a value of 0. The next group is a group of 5 where one of them gets a value of 1 over 5 and remaining 4 get values of 0. And you can imagine going in this sequence with larger and larger indices being grouped in larger and larger groups. One of these groups is assigned a value which is 1 over size of the group and others are assigned a value of 0. If you look at the PMF, probability mass function, or PDF of this sequence of discrete random variables, you will see that for this first group of 2, the PMF has equal probability of half and half for values of 0 and half, because one out of the two random variables is going to get assigned a value of 0, the other is going to get assigned a value of half. So each member of this group of 2 has a probability of half being assigned a value of half and probability of half being assigned a value of 0. The next group of 3 has a different PMF where it has a probability of 1 over 3 being assigned a value of 1 over 3 and probability of 2 over 3 getting assigned a value of 0. And the next group has a probability of 1 over 4 for value of 1 over 4 and 3 over 4 for value of 0. So as you go on and on and on, the height of this pulse at 0 approaches 1 and height of this pulse approaches 0 and location of this pulse also approaches 0. So if you assume that there are only two outcomes of this random experiment over which all of these random variables are being defined, and one of the outcomes gives a value of 0, the other outcome gives a non-zero value which becomes smaller and smaller with smaller and smaller probability. So destination random variable for this sequence of random variable is a random variable which gets a value of 0 with probability 1. And if you consider this random experiment to have only two outcomes, all outcomes go towards this destination value of getting assigned a value of 0. So this is a case of sure convergence. Let's look at the next case. This is similar case where the first random variable always gets a value of 1, and in the next group of two, one of them is picked randomly and it gets a value of 1, other gets a value of 0. Next comes group of 3 where 1 out of 3 is picked randomly and gets assigned a value of 1 and others get a value of 0. Next group is a group of 4, group of 5 and so on and so forth. If you look at the sequence of PMF for these groups, the first group has a PMF with a pulse of height half at 0 and a pulse of height half at 1. The next group of 3 has a pulse of height 2 by 3 at 0 and a pulse of height 1 over 3 at 1. You can imagine if you move in this sequence of random variables, you will eventually get a PMF which approaches 1 for value 0 and approaches 0 for value 1. So you can imagine if we move in this sequence, eventually you will get a very high pulse approaching 1 here and very small pulse approaching 0 here. So probability of a random variable far away in the sequence being different from value of 0 will approach 0. The probability approaches 1 that random variable far away in the sequence will get a value of 0. But can we say that the value of random variable far away in the sequence will also be 0? No. Somewhere down the road in this sequence, you will have a random variable which will get assigned a value of 1 with very small probability. So you cannot force the actual value that a random variable takes to be away from 1, but you can reduce the probability of that happening to a very, very small number. So this convergence is also a convergence to a destination random variable which assumes value of 0 with almost 1 and value 1 with almost 0, but it is not sure convergence. It is convergence in probability. So I hope you have a clear idea of sure convergence and convergence in probability. Convergence in probability is a weaker type of convergence and sure convergence is a stronger type of convergence. In previous lecture, we talked about other convergence criteria. In addition to sure convergence and convergence in probability, we talked about convergence in mean and convergence in the distribution. So let's talk about convergence in mean. To talk in a meaningful manner about this type of convergence, you have to know something about inner product of two vectors or inner product of two functions. Inner product of two vectors is easy to understand. It is called the dot product. The dot product between two finite dimensional vectors is summation of element by element multiplication of all the elements in the two vectors. The dot product defined for summation is usually called inner product. So inner product between two given functions fx and gx defined over the same domain is defined as integral of point by point multiplication of two functions. This is very similar to the dot product of two finite dimensional vectors. So if you have two functions fx and gx, their dot product is denoted by fx dot gx, and it is given by the formula integral of fx into gx over the whole domain over which fx and gx are defined. So if you have two functions fx and gx, their dot product is a number, a real number. Could be a positive number, could be a negative number. So suppose if you have a sequence of functions, say f1x, f2x, f3x and so on, and there is another fixed function gx, and you start taking inner products of f1x and gx, f2x and gx, f3x and gx, you will get a sequence of numbers. And if this sequence of numbers converges to a destination number which is equal to inner product of gx and some function, let's call that function f naught x. So if this sequence of numbers that we get out of a sequence of inner products converges to inner product of f naught x and gx, we say that this sequence of functions f1x, f2x, f3x converges weakly to f naught x. The convergence of random variables in the sense of mean square convergence is this type of weak convergence, where we have a sequence of random variables x1, x2, x3 and so on, and we say that expected value of xn minus x naught whole square approaches 0. So we evaluate the expected value of a derived random variable xn minus x naught whole square, and you know expectation value is evaluated as an integral, and in that integral we have x and fx, the PDF. Now we have a sequence of random variables, so we will have a sequence of PDFs, and we are going to take inner product of x and that sequence of PDFs and we'll get a sequence of numbers. If that sequence of numbers converges to 0, or expected value of xn minus x naught whole square converges, then this sequence of random variables x1, x2, x3 and so on converges weakly to x naught in the sense of mean square convergence. So mean square convergence relies on inner product, and the result of inner product converge to a destination value. Hence, this is called a weak type of convergence. The last convergence type that we discussed was convergence in distribution. That is also a weak type of convergence, and one application of that type of convergence is central limit theorem. We'll talk about central limit theorem toward the end of this lecture. Let's talk about an application of this sequence of random variables and their convergence. That is population sampling. We did talk about this population sampling in previous lecture, where we said that if we have a large population and we pick a small sample out of that large population, then we are observing values of different random variables which are actually slightly different from each other, but if the population is huge, we can assume that the sample that we picked represents outcomes of independent and identically distributed random variables. So if we have a small sample taken from a large population, can we make some measurements on that small sample to make an estimate of parameters that the probability model of the whole population follows? We certainly can try and investigate if observations made on such a small sample make sense about representing the parameters of the probability model that the whole population follows. Application of this type of population sampling are diverse, and one of them is estimation of the mean value of a whole population. Suppose you have a large university of male students and you pick a small sample out of that large population and find the average, the sample average. Does this sample average in some way represent the population mean, the mean value of the probability model that the whole population of students follow? Similarly, we can take a small sample out of a large population and ask a few questions to the individuals who were picked in the sample. Then, the answers given by this small sample, do these answers represent the answers which we could have gotten if we had asked the same questions to the whole population? Of course, it is impractical to conduct a survey of the whole population. Surveys are usually conducted on small samples. Then, is it meaningful to say that the answers of the small sample do represent the answers of the whole population? An example of such a survey is the type of survey that is usually conducted in Western countries from time to time, where they ask the individuals to assign a number between 0 and 100 as the approval rating of the president in their eyes. So, the respondents of the survey assign a number between 0 and 100. The people who totally disapprove president's policies, foreign policy, economic policy, they may assign a number 0 or 5 or 10. And people who are very faithful to the president, more faithful to the president than president himself, may assign a value of 100. Other people who a little bit disapprove president's work may assign a value of 80, 85 or 90. So the results of this small survey are tabulated together, their average, the sample average is taken, and then statistical analysis is given that says that this answer does represent the answer of the whole population with some degree of error, with some degree of confidence. So statistical analysis is not in the course that we are studying, but this type of population sampling where a small population, where a small sample is taken from a large population is used to measure the parameters about the probability model of the population is indeed in your course, and that is very interesting example to analyze. So suppose you have a large population and from that population you take a small sample and make some measurement of all the individuals in that smaller sample and find the average value of that sample. This is a random variable because if you conduct this experiment again, that is you pick another small sample of the same size, you will get a different value. So the sample average is a random variable and it is a function of the sample size. So if you take a sample of 5 individuals and take its average, let's call this random variable capital X5. You can take a larger sample, say a sample of 6 individuals, add the 6 observations, divide by 6 and get a value which is also a random variable, and let's call it capital X6. So you keep on increasing the size of your sample and take the average of that sample and get a number and assign it capital X with an index which represents the size of the sample. Now the question is, if we take bigger and bigger sample of the population and take its sample average by adding the observations and dividing it by the sample size, where does this number converge? Where does this number go? Does it converge? Does it converge to a certain value? Does that value represent some parameter of the population? The answer is yes. If you take larger and larger sample and take sample average, this sample average converges to population mean. And this convergence can be analyzed if we know a little bit about the inequalities that are very commonly used in probability theory, that is Markov inequality and Chebyshev inequality. We are going to study these inequalities, and we are going to use these inequalities to analyze the behavior of this sample average and its convergence as larger and larger sample size is taken to find the sample average. So let's study the Markov inequality first. Markov inequality puts upper bounds on the tail probability of a random variable which only assumes positive values. Here you can see on your screen a typical PDF of a random variable which only assumes positive values, because PDF is only defined for positive values of domain. So for this type of random variables, Markov inequality says that probability of this random variable whose PDF is shown being larger than a certain value c, where c is a real number, is less than or equal to expected value of that random variable divided by c. This c can be any number, and once you pick the c, you will find the probability of this tail, the integration of this PDF from c to infinity, and Markov inequality says this area of the PDF from c to infinity is going to give you a number which will be less than or equal to expected value of this random variable divided by c. We can mark different points on this PDF to analyze this Markov inequality. For example, we can pick c to be 1. We can pick c to be equal to mu x. So we can pick the ratio, this ratio, to be 1. So if we pick c to be exactly equal to expected value of x, or this ratio to be 1, then Markov inequality says this whole thing, that probability of x being larger than mu x. So area of this PDF, area under curve of this PDF from mu x to infinity is going to be less than or equal to 1. Actually, this expression does not say any new thing. Probability of any event is always less than or equal to 1. So if you pick your c to be equal to mu x, you get this upper bound of 1, which is kind of meaningless because probabilities of all events is going to be a number which is less than 1. But if we pick a different value of c, for example, we pick c to be 2 times mu x. Remember, mu x is the average or expected value of this random variable, the point around which this PDF nicely balances itself out. So if you pick instead of mu x 2 mu x to be your value of c, then you replace c with 2 mu x and you get a number half. Now Markov inequality says that probability of this random variable being between 2 mu x and infinity being larger than 2 mu x is less than half. So Markov inequality puts an upper bound that probability of any positive valued random variable being larger than 2 times its expected value is going to be less than half. Similarly, if we pick c to be 3 mu x, then Markov inequality puts an upper bound of 1 over 3 for the probability of this tail, which starts at 3 times mu x and ends at infinity. This can be summarized in this figure that you see on your screen, where markings are at mu x, 2 mu x and 3 mu x, and it says that a probability of this random variable being larger than mu x is less than 1, being larger than 2 mu x is less than half, and being larger than 3 mu x is less than 1 over 3. I have not picked a number less than mu x. For example, if I had picked a number which was mu x by 2, I would have gotten an upper bound with 2 here. So it will say that probability of random variable being in the range mu x over 2 to infinity is less than or equal to 2 which is also meaningless because probabilities are always less than or equal to 1. So we usually do not pick a value of C to the left of mu x, we always pick a value to the right of mu x. Markov inequality is important, but it is only applicable to those random variables which only assume positive values. This inequality is very simple to prove, and let's have a quick look at its proof. On your screen you see the expression of expected value of x broken into two parts. Usually expected value of x is integration of x times fx over the whole domain from 0 to infinity. Remember, we are working with those random variables which only assume positive values. But I have divided this integral of expected value of x into two parts. First part is integration from 0 to c, a certain value that we pick, and the other integration is from c to infinity. So expected value of x is sum of these two integrals. And if I drop this integral, the first integral from 0 to c, out of this equation, then the left side becomes larger and the right side becomes smaller, because all these integrations are going to give me positive numbers. X is positive because random variable only assumes positive values. Fx, the PDF, is always positive. The multiplication is positive, and integration from 0 to c is a positive number. Integration from c to infinity is also positive. Everything is a positive number. So if you drop one positive number out, the remaining expression is going to be smaller than the total expression, which is expected value of x. This is graphically shown here on your screen, where you have this upper graph as graph of PDF of x, and the lower graph with filled areas is multiplication of this PDF times x. X is this line with 45 degree slope. So when you multiply x with this PDF, you get this graph, and area under this graph, total area under this graph, is going to give you the expected value of x. One part is shown in red, which is integration from 0 to c. Other part is shown in green, which is integration from c to infinity. And the first part of the proof says that this area, this green area, which is multiplication of this PDF and this x starting from c all the way going towards infinity, is smaller than the expected value of x. If we look at the next part of the proof, then instead of using x times fx, which starts from c and goes towards infinity, we replace it with a constant value c. So a quantity which takes on values of c or larger is replaced with a constant c, makes this new expression even smaller. So this expression is even smaller than this one, hence expected value of x is certainly larger than this one. Now all you have to do is take c to the other side below this expected value of x, and you get this expression that expected value of x divided by c is larger than integration of PDF from c to infinity, which is nothing but probability of x being larger than c. If you rearrange the term, you will certainly get the result of Markov inequality, that probability of a positive random variable x being larger than c is certainly less than this expression, which is expected value of x divided by c. Now that we have seen the proof of Markov inequality, which is only applicable to those random variables which take only positive values, let's look at the next inequality, which is called Chebyshev inequality. This inequality gives upper bounds on tails of probabilities of those random variables which assume positive as well as negative values. Let's have a look at the expression of this inequality. Chebyshev inequality says that if we have a random variable x, then the probability of this random variable x being away from its mean value by a certain number c is less than or equal to sigma square x, the variance of x divided by c square. This inequality is applicable to random variables which take positive as well as negative values, the kind you are seeing on your screen. The PDF that you see on your screen is symmetric, hence its mean is at 0. Then the Chebyshev inequality says that probability of x minus mu x whole absolute value, where in this case mu x is 0, so probability of x being larger than c, absolute value of x being larger than c means x being larger than c as well as x being less than minus c. So probability of two tails starting from c to infinity and from minus infinity to minus c is less than the variance of this random variable x divided by c square. We can mark different points on this PDF, for example c and minus c, find the two tails, and Chebyshev inequality says the probability, combined probability of these two tails is less than or equal to variance of this random variable divided by c square. We can put certain interesting values of c. For example, we can put c to be sigma x or standard deviation of x. If we use this value of c and put it here, then you will get sigma x square over c square 1, and Chebyshev inequality says that probability of this random variable being in these two tails starting from variance to infinity and starting from minus infinity to minus variance is less than equal to 1. This does not convey a lot of information because probabilities of all events are going to be less than or equal to 1. But if we put the value of c to be 2 times the standard deviation and simplify the expression, the Chebyshev inequality says that probability of this tail and this negative tail combined is going to be less than 1 over 4. And if we put value of c to be 3 times the standard deviation, then combined probability of this positive tail and negative tail away from the mean by a distance of 3 times standard deviation is going to be less than 1 over 9. This can be summarized in the slide that you can see now on your screen, where different tails are shown with associated upper bounds of probability. It's very easy to follow the proof of Chebyshev inequality because it's built on top of Markov inequality. Here we see probability of y being greater than a number c square is less than expected value of y divided by the same number c square. This is exactly Markov inequality where random variable is y and the threshold is c square. If y is replaced with this new random variable x minus mu x whole square, then the new expression is shown here. And if you rearrange the terms and recognize that this expectation values of x minus mu x whole square is nothing but variance of x, you get your Chebyshev inequality. So Chebyshev inequality is built on top of Markov inequality with special transformation of y being equal to x minus mu x whole square. This Chebyshev inequality can be used to analyze the behavior of sample average and its convergence. All we have to do is replace x with Wn, the sample average. So if you replace x with Wn, you get an expression which says that probability of Wn and mu x, where Wn is sample average and mu x is population mean, being larger than a certain threshold c is less than variance of Wn divided by c square. If you replace in this equation the value of variance of Wn, which is variance of x divided by n, you get this expression which says that probability of Wn, which is sample average, and mu x, the population mean, the absolute value of this difference being larger than a number c is going to be less than variance of x divided by c square whole divided by n. In this expression, if you keep c fixed and variance of x is already fixed, you can change n. You can take larger and larger sample and make this probability smaller and smaller. So this sequence of random variables, which is wn minus mu x, probability of them being larger than a certain number c is going to approach 0. So this sequence of random variable is going to converge. This sequence of random variable is going to converge to mu x, and this convergence, because of this expression, is convergence in probability. So with the help of Chebyshev inequality, we have established that sample average converges towards population mean, and this convergence is convergence in probability. This is exactly what weak law of large numbers says. Since this convergence in probability is a weak type of convergence, this statement that if we take larger and larger samples, then sample average converges towards population mean is called weak large numbers. There is another law of large numbers called strong law of large numbers, which states that this sample average actually converges towards population mean almost surely. Almost surely is a stronger type of convergence. Unfortunately, the proof of strong law of large number is very complex and it is not included in your course. The last type of convergence that I just want to briefly mention is convergence in distribution, which is also a weak type of convergence, and you can see the statement of that convergence in your textbooks. With this, we conclude our discussion of probability theory. Starting with next lecture, we are going to discuss stochastic processes, and the first topic that we are going to discuss is going to be Markov chains. Till next lecture, I wish you the best. Thank you. Khuda Hafiz.